Okay, now maybe jumping ahead, because let me review what we did last time. I know that I didn't quite finish, but you have a handout, because as much as, I was spending just a donkey load of time on, what's it, donkey load? Anyway, donkey load of time on a lot of minutia, and there's even more minutia, that's why you have a handout. Note that I try to be incredibly clear which operator I'm talking about. Is it time dependent or not? Time dependent, Heisenberg. Heisenberg operators have time in them. Okay, so the Hamiltonian, the Heisenberg Hamiltonian, therefore it's time dependent. Operator, time evolution operator, whatever operator we're trying to work with. After all, Schrodinger operator. So if it's x, it's just x. If it's p, it's just ddx minus h bar. Right? Now, when you're solving, if this is p at a later time, heads up, it's not going to be equal to just ddx. It could be ddx plus some other jump. So that's what you're trying to figure out. And we're going to cover that today. And again, that will be applicable to your homework, the first 3 problems. And the 4 through 6 is a little bit harder because the Hamiltonian has an extra term, has a term that is making that mimics gravity. The higher up the particle is, the more potential energy it has. And that's gravity for you. Not that gravity needs a quantum mechanical treatment. It's just kind of, part of the purpose of this problem set is, in this case, it really just is making sure you're at your tippy top of math. A lot of you said you're taking spectroscopy, and that's not going to be easy mathematically. It should be about on par with this. And so it's good for you to warm up. Once you get through this, there's really nothing you can't handle. So, okay, anyway, so this was part of the derivation. I'm just showing you like the halfway point. Everything, so that's not time dependent, that is. Okay. Notice that the negative sign went away. That's by making the operator come first in the commutator. So everything is time dependent. Okay, but this is equal to the Schrodinger time independent Hamiltonian. Didn't you say that? That's equal to the time independent Schrodinger because because right, the time evolving operator is just the ones with the, well, it's right there, right? But because the time evolution operator is a function of the Hamiltonian, you can do this. So there you go. Anyway, world's simplest proof. Okay, so now you get this deal. You need to write down the final result. So this is what you find on Wikipedia. This is what you Google. Again, I'm being insanely careful. Multiple redundancies on my labels here to make sure you know that I'm not time evolving the Hamiltonian. Okay, so this is a biz knocker because what you're doing is you got yourself into DQ. So the time evolution of the operator is equal to the commutator of that same operator with the Hamiltonian. Now, where you're going to screw up is that you're going to want to make this the non-time evolving operator. X is X. And that's wrong. Now, heads up, we often can get it into, you can do extra proofs starting here to show maybe that is the case. And so you're going to see a lot of that today, but you can't start there. All right, so So how does that work? What you'll find is that you're going to do something like this. You can factor out the operators. Okay, so here's how the trick often goes. You're going to see this more often than not that this is the only way to do it, as I warned you. You can take out the time evolution operator. You're kind of actually working backwards from here, by the way. But you can factor them out. And then the prayer is that you have a formula for a commutator, because these are generally, H has got a bunch of P's, it always has P squared in it. You will never avoid that. That's the thing that sucks about it. But it may have an X too. This sucker was probably P or X. Now, momentum is commutes with momentum, but it doesn't commute with X. But I know what that is. Px is minus IH bar, or IH bar. Anyway, so again, the idea is to take these factors out. You probably actually have a known commutator at that point. And then you got to remember that these are still there, and it gets trickier. So anyway, that was our approach for this problem. So again, I'm still just reviewing because I know that that was a nightmare of algebra. It's mostly algebra, right? You have seen more than enough calc and algebra to do this. It's just a matter of doing it. And it's like, well, how would I ever know to even try this? And the answer is, well, that's why you take classes. And what I always wonder is, why did somebody ever figure out how to do this to begin with? And the answer is, well, that's why some people have Nobel Prizes and I don't. Although I should have one. For the fact that I am a good cat owner and I can move objects with my mind. Don't tell anyone I said that, that's crazy. Now anyway, okay, so, oh, come on, it's Friday, it's nice outside. Everyone's sick. Okay, so again, you see us use that trick. So, just from last time, I think it's how you do your handout. So that was our trick. And, and of course, because H is just SZ, what I've got is SX and SZ. And of course, that's IH bar SY. Right? You know what the commutators are of this sucker. Don't forget your constant, right? So this ends up being minus IH bar. The constants in a commutator just factor out. You probably just guessed that. Okay, again, multiple redundancies. SY, little s, means Schrodinger. So I have that in your problem set. Little s for Schrodinger. Of course, that means that for a Heisenberg, that's t equals 0. So actually, I'm kind of using bad terminology. Actually, I should say the Heisenberg form, just at t equals 0, which is the Schrodinger form. Anyway, so maybe I'm not using my labels correctly. Okay. All right, from here, what you get is just, actually, I don't think I just need a little bit of cancellation of units. Okay. Now you can see where, here is where you can blow it. Notice that, minus IH bar over, don't forget this, divided by IH bar, okay, cool, that's gone. Minus frequency. Okay, that's the Schrodinger operator, the one that we covered so many months ago. But it's still being time evolved, so it's actually the time evolving form, which you don't know what it is. So this sucks. You're actually at a stopping point. You can't go further. But again, the person who won a Nobel Prize for this stuff then did this. because that person was smarter than me. Well, those people are also dead. I'm not. Who's smarter now? Okay. So, you may recall, actually, early in the class, I talked about how you're going to do some mathematics, how I'm going to try to, we want to build you up on this. It's just a point of pride for a physical chemist. And I actually, one of the first things I did was I solved a couple differential equations. So you've actually seen it many, many times now. You have to do it on your homework. It doesn't matter if it's an F or a P or a T or an S. It's the same deal. So the way I did this, I did it a little differently in class. So let me, my notes, I didn't actually like my own notes, so I reworked them here. So what I like to do is I take the double derivative of this. Again, this is like the fourth time you've seen this. So now, of course, that's a constant. And again, you can see the trick is that now I'm down here. And now you've got yourself a standard Diffie cube. So these two are equal, and then the standard result from Symbolab or whatever you want to use. Now this is where I actually stopped. I'm still reviewing, by the way, but I think it's probably quite necessary. I know that was kind of hideous. So this is where I stopped last time, and even I didn't plan to stop because now you want to look at the handout. I don't want to spend another 20 minutes on algebra. What you then do, and I hinted to this, actually I made a mistake in the handout, the answer key, the problem set 8. That the way you solve this, on problem set 8, you had the same problem, and I gave you a initial condition. My answer key, actually I screwed it up, but you guys answered it correctly. I'm still grading that one. I kind of needed a break. I'm as tired as you are. I'll have your homework probably Monday. Anyway, so you run into this situation, you have to have initial conditions, but so either you know them as an experimentalist or you're answering your problem on a homework set, so you're told, or in this case, it actually should be pretty freaking obvious that, now notice what I've done, the Heisenberg representation at time equals 0, and so that way you can put a 0, so this would be A plus B. So A plus B, so this is how you go about solving it, would be, of course, the Schrodinger operator of Sx. Again, h bar over 2 plus minus h bar over 2 minus plus, whatever, or matrix form. Again, we did this. You can actually do this problem with matrices. It's kind of interesting to have unknowns in matrix form. That's kind of neat. I've done some problems like that. It's not so hard. It's a neat puzzle. Okay, so at time 0, you should have the same operator that we've always had, and then the next deal is that the derivative of the Heisenberg operator, but at the initial time, again, so let's do that. So it'd be IWA minus IWB, and that would be, sorry, with my notes. And again, you just look at the notes, and again, you can see how important it is to make sure that you always keep track of what operator you're talking about. Is it time evolving or not? Okay, and now I've screwed up because I've run out of space, so here I'm going to have to just do something stupid and just use this. Okay, with this, you now know that Initially, the SX operator is very sensible. As it evolves in time, initially, because cosine of t equals 0, cosine 0 is 1. Initially, the SX operator is just SX as we've known it. But what you see is it's evolving over time. If time goes forward far enough, cosine is 0, and sine, determined by the angular frequency, then sine will become 1. Cosine at that time will be 0. So you can see that the SX operator, if you wait long enough, turns into the SY operator. Isn't that nuts? Go figure. Again, I don't know why the book says, oh, this makes total sense. No, it doesn't. I just know that this is a mathematical construct that gives the right results. And I have to admit, so remember I was saying, the benefit is that you don't have to mess with your states, your kets. Your kets can stay just as you've always known them. You're not time evolving those bastards and leaving the operators alone. Instead, leave your states alone and then let the operators evolve. So actually, the more I think about it, the more I realize this is actually the most reasonable approach, because we're going to cover how on the computer to solve, to time evolve wave functions. And again, that's the Schrodinger picture of time evolution, what we started with. I'm going to show you how to do that on the computer. And it's actually kind of a biz knocker. So if you actually can solve the time evolution of the operators and leave the states alone, and the operators are actually, I mean, look, I know this rigmarole wasn't great, but look, we're done. And it's not ultimately that complicated, and it's actually kind of sensible. Oh, look at that. S at t equals 0 is Sx. S at y at t equals 0 is Sy. Cosine, right? So anyway, so I hope that all of this isn't, it's an algebraic nightmare, but I can guarantee that it actually is a little bit easier to do it this way than time evolving. And here's an example. So to go back to when we did the Schrodinger frame, so let's ask Sy. What's Sy for the Sx, the initial Sx plus state? And what you get is h bar over 2. And again, this is what. So again, imagine using this operator. Again, you know the Sx and Sy operator. H bar over 2 minus plus minus h bar over 2 plus minus. H bar over 2 plus I minus minus h bar over 2 minus I plus. Anyway, you remember those. They weren't. At one point you thought those were hard. Now you got something new to look at. So anyway, so you can see that this state in the S, originally in the, okay, so X is this way and it's plus, so it's pointed at you. What you're seeing is that where's the magnetic field is this way too, right? Really? Where's our magnetic field? Where's the Hamiltonian? It's up, right, it's SZ. So, remember how this is how an NMR works. Electrons, protons, same thing. They're going to be pointed up with the magnetic field, but what you do in a 2D NMR is you use what's called a pi-halves pulse, and you point it in the plus x directions. And what you're seeing here is that then it's rotating. Right? And that's what that rotating magnetic field is picked up by a copper coil. It generates a current. And that's your signal from a 2D NMR. Right, so now you see why. Now I was trying to trick you there because if the Hamiltonian was in the x direction and the state is Sx plus, what happens? Huh? What do you think would happen? If the magnetic field and the state were pointed in the same direction? Hence, all this dynamics occurs because the Hamiltonian and the state are orthogonal. So if they're not orthogonal, just take a guess. Nothing would happen. Remember, we covered that. A state of the Hamiltonian does not do what with time? It does not evolve, right? We covered that. Pure states of the Hamiltonian do not evolve in time. They don't do anything, which is crazy, because everything is doing stuff. Okay, but anyway, remember, we talked at length about that, so maybe watch why I have videos, right? You can go back and watch all of it. You might, this stuff is nasty enough that you really might want to just watch this time-dependent stuff from the very beginning, because we're kind of at the end of it today. Although I am going to go over, right, so this was spin, so remember, I've done this, I've done this a couple of times. I've been talking about spin for a long time because it's a good problem, it's easy. Electrons are quantum mechanical. You really need to understand electrons in the chemistry department. It's applicable to 2D NMR. All NMRs are 2D NMRs. But now let's do your homework. So let's do that, and that will be it for this. And then we're going to kind of go into we're going to get back to more molecular stuff because I know we've been really quite abstract. But again, remember my philosophy here was to really hit some fundamentals, which is way easy with direct notation. And when you need to learn some quantum for your problem, it should be relatively straightforward because you just have a quantum mechanical way of thinking. So I think that would serve you better. That's my hope. I don't know that, but I'm hoping it's true. Okay. So now let's do the same thing one more time, then we're going to get to vibration, and then we're going to get to atomic structure, angular momentum of atoms, which it's not that bad. There's like this little trick to understanding it, and once you get that trick, it actually is going to be easier. It's definitely easier than this stuff. Okay, so let's do free particle. So this is your first three problems. Free particle. Free wave. Okay, but my wave function won't be e to the I kx because that sucks. Okay, so we're going to have this Schroeder. So I'm subscripting it. The S for Schroeder, right? So the Hamiltonian is not time evolving. Recall that the time evolution operator, e to the Hamiltonian, only works because the Hamiltonian is not time dependent. That there are time dependent Hamiltonians, we're just not doing those. So don't forget that. Okay, so there's no potential energy. That's what it means to be a free particle, free wave. I'm just not going to use a free wave function. So that's why you're going to hate this. Okay, so let's solve the time-dependent momentum operator. And you have to start here. There's no other choice about that. Actually, wait a minute, I think there is. That problem, remember I had a problem, not the last problem set, where you had unitary operator, unitary operator is equal to a series of commutators, and you had to prove that, you had to do the derivative and prove it was correct. I think that's applicable to this. Anyway, but let's not worry about that. I'm wondering things out loud, so that's stupid. Okay, so again, I'm sorry the H is kind of small, but again, the time-dependent operator, 1 over IH bar, commutator of the operator. Okay, so what are we going to do here? All right, so in this case, I am going to, there we go. I'm going to do this. I'm going to factor the operators out. And again, just, H is the Schrodinger. I'm not going to put all that terminology. It kind of sucks to do that. Okay. Now, you as members of the class should be good enough to figure out So using the trick of factoring out the time revolving operators and hoping that you end up with a commutator that's known. What do you think? You think you know that commutator? Huh? All right. So if you're staring at the H, you're not going to get anywhere. All right, plug in your H. Operator, operator squared. What's the commutator? Right, 0. This is P cubed minus P cubed. All right? Not over 2m. Yeah, who cares? 2m doesn't matter. Right? You do see that, right? These are the same operator. The function of an operator and the operator commute. That was part of your test. It's a known thing. We've talked about this quite a bit. So all this is 0. Okay. Now, I have to admit, I am a little bit lost. I mean, it's obvious what the answer is. How to solve that? I don't know. I'm looking at this and I want to give you like a formal proof. I want to bring the dt over and integrate, but there's nothing to integrate, so I'm like completely confused. And then I don't know what to do with the partial on the other side. But anyway, what happens is, okay, the Heisenberg evolving momentum operator is actually the Schrodinger, I use the subscript, sorry, I keep changing it, don't I? Sorry about that. Okay, so there's no time evolution. So I don't know that there's anything to solve because literally nothing is happening. So again, this is the only thing that can be a little funky is when you run into this. The time evolving operator is not evolving with time, so therefore it's just the Schrodinger, just double derivative of that minus, what do we do? No, just p. So minus I h bar ddx, and it doesn't change over time. There's no t in it, right? So that's the trick. There's no t, so the derivative with respect to t is 0. Okay. Now, so this one's kind of easy. When the commutator is 0, there's literally nothing to do. Just write down the Schrodinger non-time evolving operator. Again, I hope that that's burned into your mind at this point. Okay, this is going to be different. Heisenberg, little h. This one is different because what do you think is going to happen here? All right, it is let me just write all this out. Okay, so just x, I mean it's just x, and now I've got this. Okay. What do you think? How do you go about that?
You have to transform the operator.
Well, I mean, how did you do this? Did you do this before? What was this? Yeah. And how did you do that? You've done it before. You worked through it all. You can do it again. You're just going to hate it. So this is IH bar. Now, you see the problem is, don't forget your constants, right? Now you have to do that. Fun. Then you have all the tools. All right, you're going to have Oh, you see why you're going to hate it? See that? You got a double derivative. You got a product rule. It sucks when you have a single derivative and a product rule, but you got a double derivative. Right? You can do this. It sucks, but you can do it. Okay, heads up. All right, so you can do this, right? Let me go ahead and tell you something. Because it comes up all the time. And again, assuming I'm in the Schrodinger frame, if you have a commutator of x and a function of p, it's relatively straightforward. It's I h bar, derivative of that function of p with respect to p. Okay. And, where am I at? Okay, so let's do this. So that's still I h bar is still I h bar, so I'm going to do the derivative with respect to p. P squared over 2m. I can't imagine how this could be more difficult. Factor the 2m out. And then I've got 2p. And this will I h bar over m. There you go. Get back up here. Constants. Now again, remember, because I factored out the operator and of course momentum, the Hamiltonian doesn't evolve in time, and because I factored out the time evolution operators, that is not evolving in time. So neither is this. Okay, now don't forget your constants, but now do you see where you got yourself a bit of an issue? Okay, this, I don't like doing momentum because it's a derivative. I hate derivatives. I prefer integrals at some point. But now let me ask you this. Okay, so momentum is that right? Is that right? Or did I miss something? I've done something wrong. What? I can tell you something disappeared. From here to here, something just magically vanished. What vanished? The what? You found deaf. What disappeared? The what? I'm deaf. You gotta speak up. I was mauled by a tiger on Joe Exotic's land. I'll fight a tiger. That damn thing looks at me. What? Seriously, look, it's incredibly obvious. What disappeared?
They moved the operators.
The used, okay. When everyone said it simultaneously, remember when Monty Burns was sick and all the diseases were trying to come at him at once and they couldn't come through the door? So I think all of you said the answer at the same time. But yeah, the used just disappeared. You can't do that. So what is my operator? So I wrote down the Schrodinger P, but should I have done that? It's the Heisenberg P. Right? You have to let it time evolve again. You see how this gets you? That's the part that gets you. That I was telling you, you got to be real careful of where your time evolution operators are. Whether they're outside or they're acting on the inside, you've got to keep track. So this is actually the time evolving. Now, do we have any idea how to solve that?
It's the same as the Schrodinger.
Right, we already did. Ah! Did you forget that? Go here. Yeah. You see, we did it first. So you may notice on your homeworks, I had you do one operator first and the second. Well, there's a reason for that. You have to do these in a certain order, which the Nobel Prize winners helped us that's the kind of stuff they figured out, right? So the time evolving operator is actually the non-time evolving operator. So it was okay to do that, but not for the reasons that, not allowed to just forget that the time evolving operators were gone. Okay, so there you go. All right, now last bit. So remember we were Heisenberg G is equal to, again, I'm being crazy about all my notations. Yeah, okay. Now, the solution to this is, I'm just going to integrate it in my head. So the time revolving position operator is, what you're going to want, now this is actually kind of easy to figure out, is that it's, x of t has got to have an x in it. There's no t in it. At the beginning, it can't not exist. But what it does is it picks up a term. It picks up, let me just, t over m. Now the t comes from integration, so I brought the dt over and I integrated it. And then, again, now you also see why it's important that this is not actually time evolving, because all I've done is I brought dt over, right? I'm integrating. Here, let me just write it out. Of course, x. T would be from 0 to t. Actually, I would need to put a little dash, technically. Your book is obsessed with little dashes, and it's actually kind of necessary. So anyway, so I should have wrote that out. I guess. So there you go. Yeah, so that's what I'm talking. Now that's basically the answer to one of your questions. Or it's not basically the answer, I think it is the answer. But, if you could write it out again and make it stick. It'll be good practice for when you have to do the other one, the one in the gravitational field is going to be different. And again, look at the appendix for a guide on that. Last bit is called Confess Theorem. I do see this quite often. Well, not quite often. I see it. I've seen it sometimes. It's enough that it comes up. And what we're going to use is we're going to use a Poisson bracket. Remember, Poisson brackets are considered, those are classical, but you make them quantum mechanical by just throwing an IH bar. You worked a Poisson bracket in your homework. Okay, so the idea here is for when you have way more complex potential energy. So your potential energy on your hard problem is just Z, some constants times Z. But what happens when it's way more complicated or multidimensional? So this is what you want to do here. So for H bar, now again, and you should of course assume that these are not evolving with time. You should, it's like unthinkable that your potential has momentum in it. Potential energies are functions of position. It would be crazy for it to have a function of momentum. I've never heard of that. That's why your book takes this approach. I don't think anyone's ever heard of that. Now, it could evolve in time, in which case I'm using the wrong mathematics, but we're going to do it anyway, and that's coming up in 2 weeks. But anyway, so what happens when you have a really complicated potential? So if you do this, how am I doing on time? I got 1 minute left. Is that right?
2. Yeah, good.
Okay, well, I'll be real quick here. Because this simplifies, and I'll finish it next time. Again, rolling the time, it will tell you there's not. Let me show you something that you should get comfortable with, because it's really not a big deal. Is I'm going to write out the Hamiltonian. And we'll assume, again, we'll also assume that there's no time evolution of the Hamiltonian because we've been working under that paradigm. Sorry. We've been working under that paradigm for some time. Sorry, my S's are a little small, but I'm hoping you can see that. Okay, what I was going to tell you was just do that. So it turns out that I know when we had momentum and momentum squared, you can just wipe it out. Now again, I can factor out the unitary operators. And that makes this non-time evolving. It makes it the same one as this. But I can just tell you, there's no need to do it. Just wipe it out, right? Because I think you've seen enough to know that this term is going to go away. And so now I can go back here. So again, what I'm doing is I'm writing out some major shorthand. Instead of taking out the operators, making that non-time evolving, writing out the commutator, killing this one off, and then restructuring it back. I'm just telling you that when you have a situation like this, momentum, something else, you can just wipe out the momentum and just, it's going to work out that way. So, so you can just go from there. Then what you do is, and I'll stop here, we'll do this next time. Just recall that a quantum commutator is thought to be the classical Poisson bracket, notice I didn't put little hats on anything, times IH bar. Okay, so recall that we've talked about what a Poisson bracket is. Derivative of this, derivative of that, minus derivative of that, derivative of this. Figure out what that is, multiply by IH bar, and then you got yourself a quantum. The quantum deal. Now, apparently I think this is why this is a theorem. Because you're mixing classical and quantum. So that's like dangerous. So anyway, once we do that, we're going to start there next time. Once we do that, you can go forward and calculate and show what your Confess Theorem is. Not that, anyway. So anyway, I think this is considered a bit of an approximation. And one thing that also bothers people is that there's no H bar in the equations. And that's why it's thought to be probably not correct, because anything that's moving quantum mechanically in the equation has to have an H bar. Just like any equation related to the theory of relativity must have the speed of light. If it's missing, something is wrong, or it's just simply Newtonian classical. All right, anyway, last day of our funness, right? It's all downhill from here.